Okay, let's have a class, and we will continue to talk about water. And today mainly focus is on the sorption, desorption, isotherm. So we will talk about water number 2. Will be sorption and desorption, isotherm. Remember, we finished the curve at the end of the blackboard on Thursday. We're also going to remind you to talk about that. So, first of all, we need to know, what does it mean the sorption, desorption, isotherm? So, in the older time, let's say we have a food product. This is a food product, a piece of meat or a piece of chunk of cheese, whatever you can have. It could be absorbed water. So let's go this direction. So, the sorption of water. But at the same time, it also could be released some of the water. Some of the water will be flee away. Okay, or we call it evaporated. This is called desorption. And after the food in the environment, they will reach a balanced status. And this is called equilibrium. So, after you put the food products in the environment a couple of minutes, couple of hours, it will be reached called EMC, which is equilibrium moisture content, which is a balanced status. Now, very long time ago, about like 150 years ago almost, they do those research, which is you have a closed chamber or a closed vessel. And I'm going to put a pen there. Okay, let's say this is a pen. I'll put a holder right here, and I'll put a food products. And in this pan, I will put the water solution there. And at the same time, I will put different salt. For example, I could add sodium chloride, magnesium chloride, calcium chloride, different salt products. Then, after a certain time, I will take this piece out, and I'm going to measure the water activity and also the moisture content. Now, obviously, this moisture content is equilibrium moisture content. So they do those work, and then they have this very important curve comes out, which is what I draw last time. Okay, so the y-axis is water activity, and the x-axis is equilibrium moisture content, EMC. At the same time, I also want to real quick to review the water activity multiplied by 100% will equals equilibrium relative humidity. So this is called relative humidity. So sometimes this x-axis also is ERH, and then this is also going to become 100. And we know if it's water activity, this will be 1.000. Sometimes it's 4 digits. Okay, so we can separate them into 1, 2, 3, 4. So let's say this is 1.000, 0.75, 0.5, and 0.25. And this x-axis, let's say we had 100% is all the way at the top, So you're gonna get a 50 right here, 75 right here, 25 right here, and 0 is right here. So if you do this experiment, you'll get a sorption curve. What's a sorption curve looks like? And we mentioned it briefly last time. It looks like this. This is a sorption curve. And the sorption curve, we also mentioned, it could be manually cut into 3 different areas. And we call them, so first area is monolayer. Monolayer most of the time is, we call it's a bound water, which means the water cannot free available use as a solvents unfrozen at minus 20 degrees Celsius, about like 11% in the meat products. That's what we talk. The second layer is additional layer. Additional layer. They are called loosely bound water. And the last one, we call it a capillary. Capillary water, and basically it is composed by free water, which is water can come out through centrifuge and also the filter paper. And we also mentioned some of the examples. So in the first section, the monolayer, a typical example is like chips, let's say. Let's just give an example, one example. And the second section, additional layer, loosely bound water is like a raisin or chewy ball, chewy snack ball. And the last section will be meat and the fresh produce. And we also talk about the moisture amount. So we can quickly review. Chips is low. Raisin, chewy ball is intermediate. And the meat and the fresh produce, obviously moisture amount is high. And then we talk about the shelf life. Chewy ball is relatively longer. And there's a raisin and the, chips is longer. Raisin and the chewy ball is intermediate. And the fresh produce and meat, usually we say it's a short shelf life. And we also talk about the texture. So chips is usually say it's a crispy. And second one we say raisin and the chewy ball, we say it's a chewy and moisty. And the last section of fresh produce and meat, we call it a juicy, and also we say it's a soft. So this is what we talk about already. And we also mention why we have this curve, because different category, we concern a different reaction. So the first chips section, this monolayer we worry about is a lipids oxidation. Second one, we are worried about Maillard reaction. Last one we are talking about is concerned about the foodborne pathogen. So this is what we talk. Now, we wanted to explain something to you. Remember, a long time ago, I said I asked a graduate students question. What is the moisture amount? She said it's what is the water activity? She said the amount of the water in the products. But that's actually its moisture content. However, we recognize it. Why lots of the students have this misconception? Because every day we touch meat and fresh produce. We are talking about the food products in the last capillary category. It's really very sensitive to the environment, which means they have a high amount of the moisture content. At the same time, their water activity is also very high. So it looks like it is linear. Now, why it is looks like that? This is something we need to talk about. This capillary water. We need to explain to you a little bit. So in the fresh meat and the produce, we think about these type of the products is composed by lots of these very thin capillary tube. It's like assumption, okay? Composed by these capillary tube. Now, if we learn in the physics, we know that if you put a capillary tube in a water, what will happen? The water will go up. Obviously, this water gonna go up, and then they will have a curve looks like this. And then if you talk about physics, there is a pressure here, there's a pressure here, there's an F here. This is, we call it's a capillary pressure. Now the capillary pressure related to how wide of the tube, which means it's correlated to the radius, the R of the capillary tube. And also it's related to the theta, the sigma, which is called surface tension. Now at the same time, we have a capillary pressure, but as a water we also have a vapor pressure, and there is a relationship between that. The relationship is using a formula is log E P0 equals minus 2 sigma or multiplied by V or P. That's the relationship. Now here, this P is vapor pressure of liquid. And this P0 is capillary pressure. This is surface tension, and this R is radius of capillary tube. And this V is absorbed volume. R is a heat constant. T is Kelvin, international units of temperature. So we're going to talk about that. So based on this formula, if you do a little bit of the math, what are we going to see? Because this is equals a water activity. So what we find is this water activity and this radius, there is some correlation. The correlation is the width, the wider of this radius of the capillary tube, then the water activity is higher. So they did the research. If this is only 0.1 nanometer, this water activity is very low, 0.373. If this is 10 nanometer, this is already being significantly high, 0.898. If this is 100 nanometer, the radius, the water activity is 0.989. If the radius is 1000 nanometer, which means 1 micrometer, then this will be very close to 1.00 or 0.999. And this makes sense. Like a meat product, you only need a very limited pressure, the water gonna come out. That means lower pressure easily will have a water drip. So think about the meat products. If we frozen it, then we salt it, there is some pressure gonna generate, and the drip's gonna come out. So that makes sense, okay? So this is the first thing I wanna mention. For meat products and fresh produce, we think the free water is their major components, and it is related to the capillary vapor pressure, and most time we say it's a capillary water, and it's related to the radius of this capillary tube. And the assumption is that these products compose the majority of them is millions of capillary tube. It's just an assumption. So later on, people are going to do a research. This is a sorption, okay? A sorption. But how about desorption? Which means I release water. What's the curve going to be looks like? It's very interesting. The curve will be looks like this. And this is the sorption curve. Therefore, we move on to our next topic. This is 3, this is 4, and this is 5. Sorption and desorption. You want to talk about this curve?
Dr. Sen,
Yes?
I want to, for my own sanity, when we're talking about adsorption and desorption, that's just water that gathers or is released from the surface of the food, not the food.
No, not the inside, the surface.
Right, just the
yes,
surface.
just the surface.
Okay.
They do the same thing. The food products, they put it in go back to an oven. Then after a certain time, they took it out. They measure water activity and they measure the moisture. The reason you see all these water activity standards, if you really to look at the labels, they made by different components of sodium chloride, magnesium, and calcium. They made different standards. That's what you ask for standards. That's the old time they just put the salts there and they absorbed it or dissolved it using oven and to see the curve. That's only the surface, not really the inside.
Right.
Yeah. Okay. You will see the curve is not overlapped. We call this is a sigmoid curve, and we also call it hysteresis, which means absorption and desorption is not reversible. We just make it clear, not simply reversible. So very interesting results. And I want to tell you, from the food safety standpoint, especially microbiology safety standpoints, we wish it can be justly reversible. Because if it's reversible, then the food microbiology concern will never be a concern. The foodborne pathogen will never be a concern. Think about it. I have a beef. When I don't want to eat, I have a machine. I absorbed all the water. And 1 week later, I want to cook it, or I want to eat it. I put all the water back, assuming the texture will not be changed. If this curve is completely reversed, then the bacteria will never be the concern, because when you low down, take out all the moisture, low down the water activity, the bacteria will not be survive. However, in the real life, that's not the situation. This is called hysteresis, sigmoid curve. Now, why will be looks like that? There are different theory, and you can read a different book. In Dr. Feynman's very heavy food chemistry books, they just say there are different series about it. They listed some reference you can read. In our textbook, yeah, I think it's written very well at the page, I will show you, written very well at the page 23. This is come from Dr. Ted Labuza, the ink bottle model. I think this is very easy to understand. By the way, Dr. Ted Labuza is a great American food chemist. He is a professor at the University of Minnesota Twin City. He got his PhD from MIT in 1967. And he was the last batch of the students got a PhD from MIT for food chemistry major. Later on, the food chemistry program is taken out from MIT. And so he's a very wonderful person. I met him a couple of times in the conference, IFT, IFP, and I talked to him a little bit, chatted a little bit. Unfortunately, he passed away just December 2023. A great people. And I will talk about his other things today when we talk about all those equations. So, the ink bottle model, what is the story of that? A little bit related to the capillary tube. His theory is that the sorption desorption, why the curve will be different, not completely reversible, related to the capillary water. And the capillary water is not really like these tubes. It's like straight. He thinks the capillary water looks like an ink bottle. So this is all the time the ink bottle looks like. I don't know you still meet sometimes today because you don't use those ink bottles to write anymore. People write a letter using the ink bottle, put a pen there, dip a little bit, they write. So he thinks the capillary water looks like that, which means the capillary tube looks like that, an ink bottle. So when we talk about absorption, we were major concerned about this bottle, this big R. So the water come in, how fast it is, how soon will be filled, really depends on the size of this big R, capital R, of the ink bottle. That makes sense. However, when you have a water-filled bottle, which means the water has been filled with the products, and the water gonna come out, which means the desorption, he thinks it's highly related to the neck of the ink bottle. And the neck, which is very small, that is small. That is why they are not overlap and not reversible. And I think this is a very smart model to let you understand. So it's very easy. This theory is like a meter products. They're composed by capillary tube. The capillary tube is not straight like an ink bottle. So you absorb, rely on how fast, how quick it is, rely on the large R, the capital R. And when you have this water there, then you desorption in a dry environment, it really depends on the neck. Okay, so it's really, here depends on the bottom, and here rely on the neck. That's why you will see a difference. Okay, so that's very important, something we want to mention. Now, if we do a very general conclusion, we will usually find about 3 different products. Same thing, we use a curve to express it. Y-axis, equilibrium moisture content. X-axis is water activity. There is some products, the curve looks like this. I said curve A. This is usually we call it a high growth copic products, like coffee powder. And you can see this product is highly sensitive to the environmental moisture content. Now, most of the time, what's the curve going to be looks like? The curve looks like this one. Actually, a little bit flat. Okay, this is not very sensitive to environmental moisture content. And the last one we often see in the meat products, very flat at the beginning, suddenly dropped. This is the one for high salt, sugar products. Now, why we care about these things? Why we talk about absorption, desorption? We are actually worry about is the shelf life and relate to the packaging. So that's some slides we have will be talk about later on. So okay, so we don't worry about the packaging. That's why we want to draw these type of different curves. Now, in order to talk about the packaging and talk about this situation, we were actually really concerned is about this monolayer. We are not really all of a sudden to talk about the additional layer, and we already talk about the capillary water. With absorption, the desorption, especially the absorption, at the beginning, we are going to concern about monolayer. That's what the scientific area works for the about 70, 100 years. So, next one, we want to introduce you several equations. Okay, so that will be the question number 6. We'll talk about mass equation for sorption isotherm. Okay, there are several mass equations we want to introduce. And Ian, can you move that a little bit? And we'll cover the whole area. Make sure it's covered the whole area. Is that good? Okay. We're going to introduce you with 3 mathematic equations. They all summarized by Dr. Ted Labuza in 1968. After he got a PhD from MIT, he started as a new assistant professor in University of Minnesota. His very first couple review paper summarized those 3 equations. So the first equation we want to introduce to you is called Lange-Muir equation. This Lange-Muir equation is created in 1912. Very old. It is from gas and solids. So what's the equation looks like? A divided by V equals K divided by B Vn add A Vn. Okay, that's the equation. What this means? What is A means? Water activity. What is V means? Absorption, absorbed volume. What is K? 1 divided by P0. This P0 is vapor pressure at temperature T0. We'll talk about that later. Okay, what is B? It's a constant. Heat transfer constant, whatever, it's a constant. What is the VM? This is a big thing. Monolayer value. This is a key thing here. We will talk about it. Now, this is an equation. It's a relationship equation. It is very useful. Why? Because we could have a curve. Okay, the curve I will draw is right here. What going to be the curve looks like? Y-axis, x-axis. What does y-axis looks like? Is A and V the value. X-axis is what activity? Is A. What's the curve looks like? The curve looks like this. What we are looking for here is this slope. This slope equals Vm. And we also care about here, which is the intercept. This intercept equals KBVm. So this is a little bit of math I want to introduce to you. If y equals ax at b, it's a function. What's the curve looks like? X-axis, y-axis. The slope is A and the intersection is B. So here you can easily to get it if you know this value. And at the end of the day, we really want this Vm. Why? Because if we know the Vm, we will know the area of absorption surface. It is calculated by Vm, it is calculated by Vm value. This is something I want to talk, is a mistake in the book. Divided by molecular weight of water multiplied by N0, which is Avogadro constant, and also this is a water, which is surface area. Okay, so we know that how to calculate Vm. This is 1 divided by 18. This is 6.02 multiplied by 10 to the 23. What's the value of A? I want to mention to you, this is the first typing mistake of this textbook. I want to show you something. Right here, he said, this is 10 the power 0.6 the power of 20s, and the unit is square meter. Obviously, this is a mistake. This value is the whole Earth. How many zeros there? It's 20 zeros there. And what's the final number? What he got? The textbook. The final number what they got is very low. It is only 3.5 multiplied by 10 the power of 3. So this should be minus 20. You could correct this at page 22 of the textbook. Okay, so if we do the calculation, we will get the whole thing, because 23 minus 20 is 3, so the value what we get the whole thing is 3.5 multiplied by 10 to the 3 Vm value. Okay? That's very important. That's the first mistake what in the textbook looks like. There are several other confusions. We're going to talk about that. So, here, The idea is, based on this figure, based on this equation, we could get relationship curve, we could get a Vm value, and at the end of the day, we know the absorption surface. That can be related to the packaging. However, Langmuir equation has some of the disadvantages. Because this originally talk about gas and solids, this is assumed absorption is section by section. Which means in a food products, we assume in section A, you absorb to the water, then go section B, but then go section C. But honestly, we know in the food products, the absorption will be happened all of a sudden in the whole surface, especially in the humidity environment. So, this one has its disadvantages. So in the food chemistry area, we don't think this one is really reliable. It is not really reliable. But Dr. Labuza talked about this in his review paper. Now, how about the others? The second equation we want to talk about is used a lot. This is in 1952. 1938, not 1952. 1938. Three important scientists generated equation called the BET equation. The BET equation represented by three scientists, Brunner, Emmert, and Taylor. What it looks like? What's a BET equation? The BET equation is A minus 1 divided by A. Sorry. It should be A divided by A 1 minus AV equals Vm C add C minus 1 C Vm and A. And A is water activity, V is the volume, Vm is a monolayer value, C is a heat constant of absorption. Constant, which means it's a fixed number. So we get another curve. What's a curve looks like? This curve looks like similar to that, but it's different. So what is going to be the y-axis looks like? A divided by 1 minus A V. X-axis is water activity, and this curve looks like that. So what's the slope? The slope is equals C minus 1 C Vm, and the intercept is Vmc. That is the intercept. This is a formula which is widely we using in the food products. However, there is a limitation for that. What's a limitation for that? The BET equation basically it fits a food product which water activity range from 0.1 to 0.5, which means somehow the monolayer and slightly of the additional layer loosely bound water, the products, they fit this curve. other curve has not been, other products is not well explained and covered. But it's better than the Langmuir equation because they assuming the absorption is happens simultaneously, okay? Simultaneously. So that's the second curve we want to talk about is BET equation. Okay. So we talk about the BET equation only covers 0.1 to 0.5 water activity for the products. But how about the others? This is very late, and right now we are using 9081. There is another curve comes out, another equation, GAB equation. GAB equation is created by another three scientists, Guggensen, A is Emmert, B is DeBoer. Is a GAB equation. GAB equation has two versions. The original version is calculated by little bit complicated, which is equilibrium moisture content equals WC CKAW divided by 1 minus KAW multiple 1 minus KAW add CKAW. This is GAB equation. And here WC, C, and K, these are all constant. Now obviously AW is water activity. And this formula could cover the food products from 0.1 to 0.9 water activity. And later on, there is a modified, or we say, advanced GAB equation. Modified advanced GAB equation could well cover the food products from 0.1 to almost to 1.00 water activity. This I'm not going to introduce to you. It's slightly more complicated. So here we do know there is in the history there is a little bit of development of this equation to explain the absorption, desorption. And Dr. Labuza has his review paper summarize the Langmuir equation and also summarize the BET equation. And in 1981, GAB equation is later on comes out. So right now, GAB equation is most widely used, and the BET equation is still used quite popular. And we also have developed a lot of software could calculate the absorption, desorption, and relate to the monolayer value, and also relate to the sorption surface. But the idea back of that is for develop a packaging machine. And the packaging material, what type of the material need to use for this packaging. Okay, so this is something I want to mention. Question number 7. So it's very interesting. We talk about the monolayer and the additional layer. And we talk about is water activity, moisture. But we haven't mentioned one thing. We have this curve right here, is water activity and the moisture. But we forget one important thing, the impact of temperature. So we want to mention to you is impact of temperature for impact of temperature for absorption desorption. And we can also say the impact of the temperature for water activity at a fixed equilibrium moisture content. Okay. Now, related to this temperature, we would love to talk to you a little bit, to review a little bit of physics knowledge. We talk about this constant K. We say this is 1 divided by P. Is the vapor pressure at a temperature T0. You always remember, for all these formula, when we talk about the temperature, we using the unit is not degree Celsius and degree Fahrenheit. Remember, degree Fahrenheit is very popular in United States. You also always talk about degree Fahrenheit. In China, we always talk about degree Celsius. But here, this formula, it is not. We'll talk about this Kelvin. So before we talk about this guy, we want to talk to you a little bit about that. The relationship between degree Celsius and degree Fahrenheit, we know, is degree Fahrenheit minus 32 multiplied by 5 and divided by 9 equals degree Celsius. That's just a common knowledge. But what's a Kelvin is? This is a international temperature unit used in physics and the chemistry area. What is that? K equals degree Celsius at 273. Okay, that means 0 degrees Celsius is 273 Kelvin. Most of the time we say the 273 Kelvin. Okay, so that's a background knowledge we want to talk. Now let's go back to talk about what is the temperature impact for absorption.